Okay, so just as a reminder, kind of as where we are in this lecture, we've talked about the cerebrum. We went through and we talked about the diencephalon, and we talked about the brainstem. And so because we have so many of the cranial nerves, again, that are coming out of especially the brainstem, I went ahead and included this slide. You don't need to know the cranial nerves for lecture, but you do need to know them for lab. So that was why I actually included this here. And then, again, we're going to get into that fourth section of the brain in just a minute, the cerebellum. But I just wanted to show you, again, this is kind of a nice picture that you can use for lab purposes. Again, I'm not going to test you in lecture on these cranial nerves per se for the brain lecture here, but you will need to know them for lab. So when you're going through, again, like I always think these mnemonics, so we're going to talk about why these mnemonics work when we get to like long-term memory here in just a minute. But I think the easiest one for me, maybe it's just because I kind of grew up with it, is the OOO, to touch and feel very good, velvet, aha. There are dirtier versions of that. If it helps you to remember the dirtier version of it, go ahead, whatever works for you. But obviously I'm presenting the cleaner version of this. So there's the O again, O, olfactory nerves, O, optic nerve, O, oculomotor, and then there's the trochlear nerve. The A is abducens. And then F is facial nerve. So again, you can kind of go through and see they've got, oh, sorry, I missed one. I knew I missed trochlear and trigeminal there. So you've got trochlear, trigeminal, abducens, facial, vestibulocochlear, which we're going to talk a lot about the vestibulocochlear nerve when we get to the special senses. And then glossopharyngeal nerve, vagus nerve, accessory, and hypoglossal. So again, I think this to touch and feel very good, velvet, aha. Or you can do ah or aha if you want to make sure you remember that hypoglossal nerve. But that's a good way to kind of remember the order of them. And then this will help you because this diagram actually looks a lot like our brain models. So hopefully this diagram will really help you that. I don't want to spend too much time on that because I know I have so much to talk about in lecture, but it is here. And so that hopefully will help you with the cranial nerves. I found it helpful when I was a student. Okay, so we're going to get into this fourth part of the brain. Remember, we break up the brain into these four different parts: the cerebrum, then the diencephalon, the brainstem, and then the cerebellum. So let's get into the cerebellum, talk about what the cerebellum does, and then what happens when the cerebellum is dysfunctioning. And of course, with the brain, that's kind of how we learned what we did about the brain, is by looking at dysfunction of different areas of the brain. And we're like, oh, well, when that part of the brain isn't functioning, then we can't do this activity, or we can't do this behavior. So that's actually how we learned about the brain, was through dysfunction, which is kind of an interesting and backwards way, right, to learn about things. But that's what's most easiest for us with the brain. So when we look at the cerebellum makes up about 11% of the brain mass. You don't need to know that. I'm just giving you that as an idea so you can picture about how big your cerebellum is. It's located dorsal to the pons, and then dorsal to medulla as well. So again, you're in the back portion of the brain here, and so here's your cerebellum right back here, right? Your cerebellum is going to be back here. And so it looks a little goofy when they just take out the cerebellum, because this is what it looks like if you were just to remove only the cerebellum. And the two cerebellar hemispheres here, so you've got a right and left half, are going to be connected by this area in the center called the vermis. So this is the vermis right here. And then when we look inside the brain, you're going to see that we have, again, this kind of gray outer cortex that we call the cerebellar cortex. So again, we have that gray cortex, cortical matter. And then in the interior here, we have the arbor vitae, which is where you're going to have your white matter. That's where you're going to have your myelinated tracts running. Okay. So that's kind of the makeup of the brain. And they call it the arbor vitae. Arbor means tree, vitae means life, because it literally, I mean, if you look, this is an actual cross section of a brain, and it literally looks like this tree, right? So that's why they called it the arbor vitae, the tree of life. And so again, hopefully that will help you remember the arbor vitae. When you look at the function of the cerebellum, this is where it gets interesting and fun. So the cerebellum is taking in input from your cortex, from the brainstem, and then also from sensory, especially proprioceptors. And it's going to bring in all of this information to basically coordinate and time all of your skeletal muscle movements so that you have these more coordinated and agile skeletal muscle movements. And I'll show you how important that this is in a minute when we talk about what happens when that's impaired. So again, this is going to correct your voluntary muscle contractions. You know, if you're a little bit off, you know, from where you went to grab your pen, your cerebellum is correcting those muscle movements so that you can properly pick up your pen. And it's timed just right when you go to write, okay? So that's the type of stuff that your cerebellum's doing. Again, it's kind of like this checks and balances. And I like to picture your cerebellum kind of like the autopilot of a plane. And so what it does is it's taking in sensory information to see where you actually are in space in comparison to where you're supposed to be going, where your planned route is, right? And so it works just kind of like the autopilot of a plane. That's basically your cerebellum. It's the autopilot of your plane, of your skeletal muscle movements, okay? So it's going to help us really coordinate a lot of these activities like driving, typing, or playing the violin. And when that cerebellum is impaired, it's going to be very important for you to understand that when it's impaired, you can't do these coordinated activities like driving. And you probably already know where I'm going with that. So again, also the cerebellum is going to play a major role in our sense of balance or our sense of equilibrium. And so it's pretty simple on how the cerebellum kind of fine-tunes our motor activities. Again, it's going to be taking in information from the cerebral cortex of our intent to initiate certain voluntary muscle contractions, okay? So again, if we're going to drive and take a right turn, okay, then the information that says, okay, we're going to be moving our hands to move the steering wheel to make that right hand turn is going to be sent back again to the cerebellum from, again, the cerebral cortex. Then it's also going to receive sensory reception from our proprioceptors, you know, in our hands and our arms to tell the brain where visually are our hands in comparison to where we want them to be, okay? And so again, and that's always happening. We're always sending that information to the cerebellum, that proprioception information on where, again, we are spatially, okay? And where our limbs and parts of our body are spatially in comparison to each other. And then the cerebellar cortex is going to make its calculations, okay? It's kind of like a little computer making its calculations, or like the autopilot, right? Making its calculations to find the best way to kind of smooth out those muscle contractions, again, so that they're very calculated and, again, keeping us on the track that we want. And then it basically sends this kind of blueprint of the coordinated movement to that cerebral motor cortex, okay, and to some brainstem nuclei, but you can picture, again, that cerebral motor cortex. And then the motor cortex will send the motor information out to the muscles to actually do the contraction. And all this is happening in an instant, right? I mean, you never think about all of this information having to go back and forth and be filtered through the cerebellum. It's just amazing that all of this happens in such a short amount of time. So again, I'm going to stay really basic on this in terms of what's happening. Mainly, again, I just want you to know that it's receiving impulses. You don't have to know this kind of step-by-step process, but that it's receiving impulses from, you know, the cerebellar cortex, sending information to it on what we're going to do, what type of muscle contraction we're going to do, from proprioceptors and sensory receptors, telling us where and what's happening with our limbs and things like that. And then also, again, is sending information to the motor cortex before it gets out. So it's kind of interesting, like all that happens. Now, the easiest way to remember what the cerebellum does is to remember what happens when you inhibit the activity of the cerebellum. And one of the easiest ways to picture that is if you've ever been intoxicated. Or seen someone that's been intoxicated. So if you've ever seen someone that's been intoxicated, they have inhibited, especially, the more you drink, the more you're going to inhibit your cerebellum. And so this is why you shouldn't do coordinated activities like driving, because what that does is that inhibition of the cerebellum, and especially if you're really intoxicated, can cause what's called ataxia, which is the loss of the ability to coordinate your muscle movements. So this is why, again, if you're pulled over and a police officer thinks that you were drinking and driving, they're going to ask you to do some coordinated muscle movements, like walk heel toe on a line, or try to touch your finger to your nose. And again, if you are really intoxicated and your cerebellum is really, the activity is really inhibited, again, your cerebellum can't refine those muscle movements, and you'll end up doing this, touching your eyebrow instead of your nose, because you don't have those coordinated muscle movements. So again, really a lot easier to kind of picture what the cerebellum and how important the cerebellum is when you don't have the full function of that cerebellum. Also, again, of course, if you actually have damage to the cerebellum, that can result in ataxia as well. So you lose the ability to coordinate muscle movements and things like that. So if you have a certain disease that's attacking the areas, neurons in the cerebellum, that can cause ataxia, or again, if you have actual damage to that, like if you had traumatic damage. So again, just kind of interesting. Now, what's interesting is that we also, some of the newer research has also shown us that the cerebellum actually has some cognitive functions. So I'm not going to test you on this as much because I want you to know the main role of the cerebellum, but it's kind of interesting to know that the cerebellum, we're learning, has more than just this function. And that's what's happening with a lot of the parts of the brain. We're finding out that we thought it only did this one thing, but actually did more than what we thought. And again, we find that out when people have, a lot of trauma to a certain area of the brain. So what's happened is now we have this capability of doing neuroimaging. And some of that neurofunctional imaging that we can do actually suggests that the cerebellum plays a similar role in coordinating our higher thought process, like thinking, language, and emotion. And so just like it does for the motor skeletal functions, it'll actually kind of compare our actual output for these certain functions like thinking and language with the expected output of what it should be. And then it tries to adjust it accordingly. So again, it's just like we talked about that autopilot, fine tuning a lot of these processes so that we stay on track. But it's interesting that it doesn't just do that with our skeletal muscle contractions and our movements, but it's also doing it with some of these higher cognitive functions. So really interesting. Okay, so we're going to kind of leave those behind now, the 4 parts of the brain, and then we're going to talk about these 2 functional areas of the brain that just had too much overlap with different areas of the brain to kind of separate them to like one area or another. So these 2 systems that we're going to talk about, the limbic system and the reticular formations, are going to be areas where we have networks of neurons that are spanning across really wide areas of the brain. So it's not necessarily just the cerebrum or just the midbrain. It's spanning across these different areas. And you'll see that, especially, we kind of talked about that with the reticular formations, spanning across a lot of different areas, especially throughout the brainstem. So it's not just, in one area. So that's why these 2 systems are separated out as kind of our functional brain systems. So we have the limbic system and the reticular formation system. So let's talk about our limbic system first, or our emotional brain. You can see again, here's all the different parts of the limbic system. You can see that again, it's spanning across quite a few different areas of the cerebrum here. So, and there are quite a few parts to the limbic system. You do not have to know all the parts. I'm going to mention a few of the really important parts, the cingulate gyrus and the amygdala, but again, you don't have to know all these parts. It's just too much, right? You could take a whole class on neurology. So as you can see, now that we've gotten into this, we're really simplifying the brain, but that's just because it's so complex. So when we talk about the limbic system, you really think of this as your emotional brain. And I don't know if you guys have seen this movie, if you have kids. I can't remember the name of it now, but it kind of is a movie where they kind of separate out the emotions. And so you got, anger and fear here, which I think perfectly describes the limbic system. So when you look at the limbic system, the amygdala, and here would be the amygdala right here, is our area of the brain that's really critical for responding to, again, perceived threats with either fear. Okay, so either we run from the scary bear or anger. We're like, no, we're going to stay and fight. Okay, so that's kind of your amygdala. Is do we look at these perceived threats and respond with fear or with anger? Okay, which one is it? And so that's, again, part of that emotional response that you have to a perceived threat. It's coming from the amygdala in the limbic system. So again, this is our response to anger, danger, and our fear responses. That's all coming from the amygdala. So I like this. If you've seen this movie, this is perfect for the amygdala. The cingulate gyrus is going to play more of a role in kind of expressing our emotions through certain gestures that we might make. If you, for example, you're not feeling very comfortable, you might cross your arms, that's kind of a gesture that's expressing an emotion, like a very kind of a closed emotion there. Like I'm not wanting to, give any more than what I'm giving. So there are these nice, obviously you can do it, there's lots of facial expressions that are going to express emotion, and our cingulate gyrus is responsible for a lot of that. Our cingulate gyrus is also responsible for helping us to resolve mental conflicts when we're really frustrated. So that ability, obviously you can picture this as it's underdeveloped in, toddlers, and they're not able to really resolve that mental conflict when they're frustrated and they just lash out. They don't know what to do. They just lash out again with that amygdala and anger. And that's because, again, this cingulate gyrus isn't fully developed yet. Also, our limbic system contains our smell brain. It's more formally called the rhinencephalon. Again, I just didn't want to give you another term that you had to know. So basically, all you have to know is in the limbic system, we have this area. Again, a lot of times we call it the smell brain, that gives us an emotional response to odors. So that will, again, go through the limbic system here. And so, for example, this is when you look at a skunk and you're like, ooh, that smells bad. Hey, you make that emotional response. If you've ever smelled a skunk, you can make that emotional response. And immediately you're like, oh. Or, if you have that grandma that cooked a certain type of oatmeal cookies, and you all of a sudden smell those oatmeal cookies, and it just reminds you immediately of your grandma. You have that emotional attachment to that smell. That, again, is going to be the limbic system. Now, what's interesting is most of the limbic system output is actually relayed down through the hypothalamus. And if you remember, the hypothalamus is responsible, again, for releasing hormones that control a lot of our organ functions, our visceral functions. So what ends up happening is if we're under severe emotional stress because of the limbic system, again, the limbic system's really, overactive and triggered, then that can oftentimes, because it's being relayed through the hypothalamus, result in some physical symptoms like, you might have heartburn or, again, a higher blood pressure when you're under severe emotional stress. And so, again, that's because the limbic system routes through the hypothalamus. So again, kind of interesting when you think of, if you've ever experienced that. And you can consider this emotional stress, again, even being stressed out with, exams and final exams, and you have an emotional stress to that, right? And so that's when you can get that heartburn and that higher blood pressure as well. So the limbic system is also going to interact with our prefrontal lobes. And so again, these areas that are associated with these higher kind of cognitive processes. And this is going to allow us to react emotionally to things we consciously understand to be happening. So again, you see your child walking for the first time, and that's consciously happening, and then immediately you have this emotional response. That's because of the connection between the limbic system and the prefrontal lobes. And then this also makes us consciously aware of the emotional richness of our lives. So you can imagine that if there's damage to the limbic system, then many of these individuals really struggle with, this emotional richness, this purpose of life, our lives. So that becomes a challenge when individuals have damage to the limbic system. Hippocampal structures. So there are hippocampal structures along with the amygdaloid body are actually going to play roles in kind of converting new information into long-term memories. So because of that, and we'll talk about this when we talk about long-term memories in just a minute, but because there's this tie with the limbic system for long-term memory, if you can form an emotional response to certain information, you're typically more likely to commit it to long-term memory. So kind of interesting. So if you're learning information, like for example, if we're learning about a certain disease and your uncle had that disease, you probably are more likely to commit that to long-term memory because you can make that emotional connection versus if we're talking about another disease and you don't have any family member that has that disease. And that's partly why also I talk about certain diseases, because many of you have a certain connection to some of these diseases. And hopefully if you understand and have an emotional connection to that disease, then you might actually remember what happens when, that portion of the brain is working functionally versus in that disease case. So that's part of why we talk about so many of these disease cases with certain areas of the brain. So the second kind of functional brain system that we're going to talk about is the reticular formations. And the reticular formations are a big portion of them is going to be involved with this whole process called the reticular activating system, the RAS system. And this is the system that's going to be responsible for basically our arousal and alertness of the cortex, the cerebral cortex of the brain. So these areas, and again, they're going to be scattered all throughout the brain stem. There's the reticular activating systems, reticular formations scattered, these little gray matter areas scattered all throughout the brain stem. And so that's why we talk about them, because they're not in one specific area. That's why we talk about them here as a functional brain system. And so again, they're going to be constantly sending impulses to the cerebral cortex to help kind of keep it conscious, keep it alert, keep it awake. And then it will also enhance our excitability. So this is also what will arouse us from sleep as well. So for example, when you're sleeping and all of a sudden you hear your, fire alarms going off, you immediately are going to be aroused. And that's going to go through these reticular activating system, that RAS system, to awaken you from sleep. So for example, like the sound of that alarm, an auditory signal like that will stimulate the RAS. Also visual, like lights flashing, okay, will also alert you as well. Now the challenge is that there is no input. So you have visual inputs and auditory inputs, but you have no input for your sense of smell. And this is why we have fire alarms. This is why you need to make sure that your fire alarms are functioning. Because if your house fills up with smoke, you would think, oh, I would surely wake up from that like horrible smell of the smoke. But no, you won't, because your RAS system is not connected to any olfactory input. There's no olfactory input. And that is the whole reason why you have fire alarms in your house. Again, the sound of that alarm will wake you up, but the smell of the smoke won't. So just kind of really interesting. Why we don't have any input for olfactory is as good of a guess as yours is. We don't really know. But the reticular activating system also allows us to maintain consciousness. It helps keep us awake with stimuli coming in from our ears and our eyes, even skin, touch, again, moving our muscles. And so this is oftentimes the reason why I'm one of these cases. Not everyone's this way, but I like to study in a busy place. So I loved to study when I was studying in college in coffee shops or library where at least there was some activity going on around me, because that stimuli helped keep me awake. It helped keep my brain aroused, and I just was able to study better. Again, this isn't for all people. Some people this is too much stimulus and you're not able to function. Sometimes the library is a better kind of mix, because usually a library is quiet, but there's still stimuli going on around you to help keep you, awake. So again, sometimes people like certain music going on, like maybe some, soft music in the background. Again, that music sometimes is enough to arouse the cerebral cortex. So again, interesting when you're talking about different ways of studying as well. The other thing that the reticular formations do is they filter out these kind of repetitive stimuli and weak stimuli, such as like the clock ticking. You might hear a clock ticking like when you first walk into a lecture hall, but as the lecture goes on, that gets filtered out. And so it's through these reticular formations that information is filtered out. Now, what's interesting is the drug LSD interferes with this damper effect of the reticular formations, and it promotes this kind of sensory overload. And so that's that sensory overload that individuals get when they have done LSD. This is just kind of talking about how the reticular formation system works. It's really pretty basic. Again, sensory axons are going to come in synapse in these reticular formations that are part of the reticular activating system in the brainstem. Again, they're scattered throughout the brainstem. And you can see you're getting visual impulses, auditory impulses. You're getting impulses, again, from sensory, touch, pain, temperature, things like that. And so again, as they come in, then as that sensory information synapses with these reticular formations, neurons in those reticular formations, those RAS neurons are then going to relay that sensory stimuli, up through to the cerebrum, again, obviously through that relay center, the thalamus, right? So this kind of reminds you that thalamus is a relay center. And then it will relay that information on up through these RAS neurons. And then this continuous stream of sensory stimuli through, again, those RAS neurons is what's going to keep the cerebrum aroused and alert and awake. Okay? So kind of pretty basic, but interesting in how all that happens. RAS obviously is inhibited by sleep centers, especially when you're in a deep sleep, right? And so these sleep centers are located in the hypothalamus. And then obviously it makes sense that these would be depressed by alcohol or like sleep-inducing drugs, tranquilizers, things like that. So again, those will keep they will kind of dampen that RAS system, and it won't allow you to be aroused as easily. Okay, so that's why like an individual that's been drinking, like will be talking to you one moment and then they're like asleep the next, and then you can't like wake them up. You're like, come on, wake up. Okay, that's because their reticular formations that are through the RAS system are inhibited. Obviously, then you take that to the really severe extreme side, and severe injury of these reticular formations will result in permanent unconsciousness and coma. So kind of interesting. There is a motor function for the reticular formations. They do help control some of our like coarse motor movements, as well as some of our autonomic visceral motor functions. Again, motor functions for certain organs, like again, the heart and respiratory centers. But again, this is kind of a secondary function. So I'm not going to test you on this because we have so many other areas of the brain that impact motor function. I just wanted to show you again, there's so much crossover, but I'm not going to test you on the motor functions in the reticular formation because again, it's kind of secondary to some of its other big functions. This is just kind of a nice kind of review if you want to look through this chart. It's a nice review of the different functions of different major brain regions. So I put that up there in case you wanted that as a nice little review. So the last thing that we're going to talk about is these higher mental functions. And so these are going to be things where, again, we are going to look into the analysis of how things like language happen and what areas of the brain are involved, memory, brain waves, and EEGs and what those are, consciousness, and then sleep and wake cycles. So let me go ahead and jump into this because this is just some interesting stuff. But again, I'm not going to get into the nitty-gritties of these higher mental functions because they do get really, really complicated. And you, again, could do a whole course just on these. So let's talk about language. So we've already talked about language quite a bit in terms of, I've already talked about Broca's area and Wernicke's area, but I kind of put it together here for you at the end. So remember that different aspects of language are going to be controlled by different cortical association areas, and it's usually in most individuals on the left side if you are a right-handed individual. So Broca's area, I want you to think of Broca's area as the motor speech for language, and Wernicke's area is kind of the sensory speech for language. So Broca's area is the motor speech. It's controlling, again, the ability to do all of the muscle movements that you need to do to produce speech. Not speech. And so patients, it's easiest to understand, again, what Broca's area does when you look at patients that have lesions in Broca's area. And patients that have lesions in Broca's area can understand what you're saying to them, okay? But they are not able to speak to you. So again, they don't have that motor function to the muscles that are required to be able to speak. So everything's going on correct in their brain, right? They know what they want to say, but they just can't physically say it because that's, again, damage to that motor speech. So this is what we call non-fluent aphasia. Again, non-fluent aphasia would mean that they can understand words, but they do not have the ability to speak. They've lost the motor input to, again, control the skeletal muscles for speech. So that's non-fluent aphasia. Now, Wernicke's area is, again, this sensory speech. It's our ability to understand speech that's coming in, right? That sensory information that's coming in. So our ability to understand both spoken and written words. And the easiest way to picture this is to picture a patient that has a lesion in Wernicke's area or had damage to Wernicke's area. And so they can speak, but their words are nonsensible. So we call this actually fluent aphasia, or in clinical settings, you'll hear people say word salad. And that's because they're literally just speaking. I'm going to try to go ahead and see if I can pull up this YouTube video for you because it's really short. But literally, again, so this is fluent aphasia because they can speak, but I don't know if I'm going to skip my ad here. Here, let me skip this. So they can't. They are just speaking random words, and they think they're making sense.
Hi, Byron. How are you?
I'm happy. Are you pretty? You look good.
What are you doing today?
We stayed with the water over here at the moment and talked with the people for them over there. They're diving for them at the moment. They'll save in the moment. He'll have water very soon for him. With luck, for him.
So we're on a cruise and we're about to
We
get to
will
June.
store it right here and they'll save their hands right there for them.
And what were we just doing with the iPad?
Right at the moment, they don't show a darn thing.
With the iPad that we were doing. We, like here?
I'd like my change for me and change hands for me with happy.
So again, this is a great example. You can watch the whole video if you'd like. I have the link there, but this is a great example of fluent aphasia. I'm gonna plug my headphones back in here. You know, it's just this, they think that they are making sense when they're talking to you, but their ability to understand that language, the things that you know are being said to them, and then make sense of what they're gonna say back, it is basically broken. Okay, so that's called fluent aphasia. Oftentimes, again, in clinical setting, they'll call it word salad. So kind of interesting. Those are the two major areas that are associated with language. Now we can also talk about brain activity, and we can actually look at the electrical activity now that you know, again, there's electrical activity going on in the brain as, again, neurons are firing and we're getting those changes in voltage right across the membrane. So we can measure that electrical activity of the neurons in the brain with what's called an EEG, an electroencephalogram. And this EEG, again, will help us to kind of understand what's going on with brain function in terms of the electrical activity. So usually you put electrodes on the scalp just like this, and they can measure the certain electrical potential differences between like different areas of the cortex. And so typically you'll see kind of these peaks and troughs again with the different patterns of electrical activity. And they usually, this is a little more than you have to know, but they use, again, hertz to measure the wave frequency. So each person's brain waves are going to be unique to them, okay? But we do have some of these kind of typical patterns of brain waves that we see. Now, what your brain waves actually look like, your normal alpha waves, beta waves, might be slightly different from individual to individual, but they're going to have these kind of basic same patterns. So let me show you kind of what these look like. So the first type of waves that you have are called alpha waves. And this is when you're really relaxed, you're really calm and in this kind of relaxed state of wakefulness. So you kind of see these like regular and rhythmic, low amplitude, kind of very slow asynchronous waves. Again, they're kind of, again, pretty regular in their interval. And this usually indicates, again, that our brain is kind of idle. So again, you might picture this being like if you're in a meditative state, or like if maybe you're watching TV and you're just like totally zoned out, okay? You might have these, more of these alpha waves. Beta waves are more of what you're going to see. You can see, again, there's kind of more irregular waves occurring here. Still somewhat rhythmic, but again, you may see changes in the amplitude as well as the frequency of those waves. And that's going to happen when you're, again, awake and more mentally alert. So maybe you're reading or doing a math problem. Again, you're going to see more of those beta waves. Theta waves they're really uncommon in adults. I should say awake adults. We will see theta waves as we fall into different levels of sleep, but they're more common in children, and especially in children that are having like kind of an emotional response. So we'll see these theta waves. And then delta waves, we'll talk about those theta waves. Again, you can see they're kind of pretty somewhat regular, but again, we have these really different amplitudes in them. And then we have our delta waves. Our delta waves are going to be associated with deep sleep. So this is when our reticular formations, our reticular activated system is kind of dampened. And so we see this during deep sleep, during anesthesia. If an adult is awake and has delta waves, this is bad, okay? Because this oftentimes indicates some pretty severe brain damage. So again, this is something that we should not see in an awake adult. And if we were doing an EEG on someone and they were awake, this would be a really, really bad sign in terms of brain damage. So these, again, EEGs are really helpful for us to be able to look at and diagnose certain kind of conditions. So for example, obviously you can picture they'll use them to monitor epilepsy as well as sleep disorders to see what's happening again with the electrical activity of the brain at night. Also, when the case where I have actually seen EEGs done is when I did the clinical research for multiple sclerosis, and EEGs were done to look for lesions in certain areas of the brain and associate that with possibly certain loss of function. So again, multiple sclerosis, if you kind of remember, is where you're going to have active attack on the actual central nervous system, the neurons in the central nervous system, and especially the myelin sheath, and then the actual axons themselves. So you can see those areas of damage or lesions on certain MRIs, but you can also, they'll show up oftentimes in EEGs if it's impacting, again, some of that electrical activity of the brain, which is oftentimes the case in individuals that are having severe MS attacks. So again, it'll show us the localized lesions, tumors, infarcts, areas where, again, you have cell death because of lack of blood flow, infections, again, abscess being a big infection. So again, those are the types of things that you can use EEGs to diagnose. And then, of course, it's also used in research as well as to determine brain death. We can use it to determine clinical brain death. A flat EEG, which is no electrical activity, is clinical evidence of brain death. And so they will use that oftentimes to help, determine whether or not an individual is clinically considered dead. On that serious note, we can also talk about consciousness. So consciousness is basically kind of our ability to, again, perceive sensation, do voluntary initiation of control of movements, and a lot of this higher mental processing that we can do. We associate that with someone that's conscious, right? And obviously there are clinical degradations, not degradations, but clinical gradations, that was a better word there, of consciousness. So, you can have someone that is really alert, or you can have someone that's drowsy, you can have someone that's more in a stupor, and you can have an individual that's, basically unconscious in a coma. So we have kind of these different levels of consciousness or gradations of consciousness. So again, we really kind of talk about consciousness in terms of the clinical aspect of it. So more for talking about what happens when you're unconscious. So, except obviously during sleep, loss of consciousness signals, an impaired brain function. So sometimes, again, this is just very brief. So if that loss of consciousness is brief, we call it syncope, which is just a fancy word for fainting. But you should know the term syncope because it's used quite frequently clinically. So I want you to know the term syncope. Again, just a brief loss of consciousness, you fainted. A lot of times this is due to inadequate blood flow to the brain. So again, it might be due to low blood pressure from, some major traumatic injuries. You lost a lot of blood and that decreased your blood pressure to the brain. Sometimes severe emotional stress can cause a drop in blood pressure. And then there's also these conditions where you have what's called vasovagal syncope. So, for example, if you see an individual, this oftentimes happens more when we have an emotional attachment. Like you see your husband cut off their finger and they're just bleeding and you're like, whoa, I just am going to pass out. And you just have this immediate drop in blood pressure. Not enough blood is getting to the brain and you pass out. That's called vasovagal syncope. It has to do with the vagus nerve. That's what we call it, vasovagal. Vaso being, again, that drop in blood pressure. And so an example of this vasovagal syncope is, I know my husband loves that I just share this, but is that micturition syncope that my husband had. So again, he was on a business trip, and I know you guys have kind of heard this story, but he got up in the middle of the night to go to the bathroom. He didn't remember that he had gotten up to go to the bathroom. And then all of a sudden, he woke up in a pool of his own blood, which is pretty traumatic, right? On the floor in the bathroom, he'd actually hit his nose. He broke his nose. He hit it on the bathtub. But he just woke up and he was in a pool of his own blood. And he's like, what is going on? He's like, I didn't even have anything to drink last night. So, he had no idea what was going on. So immediately they took him to the hospital and they did all this testing on him. And of course he was super healthy. And they ended up tying it back to the fact that he's over the age of 45. It's more common in men over the age of 45. And he has kind of a naturally low blood pressure and lower heart rate. So it put him in the perfect condition for this thing called micturition syncope. And we know that he is vasovagal. He sees blood and he passes out it too as well. But so again, he got up, micturition is urinating. So he went to urinate and immediately caused a drop in blood pressure for him. It was too rapid and he passed out. So again, obviously it was a very brief loss of consciousness. He immediately woke up, but unfortunately after he broke his nose on the bathtub. So there's my interesting story for you on syncope. Hopefully you'll never forget the word syncope now. So, and then here's a video if you want to see, it's just a funny one from Scrubs with JD and his vasovagal syncope. So if you want to see that, it's kind of a funny one. And then obviously coma is when you're unconscious for an extended period of time. So again, this is not the same as deep sleep. Your oxygen consumption is going to be way low. Your brain activity is different in a coma than it even is in deep sleep. And then obviously brain death is at the point that you consider an individual with irreversible coma. So again, you don't really have any activity going on. So you do an EEG and there's no activity whatsoever. Again, that's considered brain death. And this is really challenging because this has kind of ethical and legal issues surrounding this in terms of whether a person is really dead or alive, especially if we're, keeping them, if they're in this case here, and we're keeping them alive, like physically their organs are still able to function and you're, able to provide oxygen for them. Again, their brainstem is still taking care of all of those reptile major functions to keep them alive. But technically they're brain dead. The EEG shows no brain activity. This is a tough call again for clinical situations. So again, a lot of challenging ethical things that are associated with that. Sleep and wake cycles. Of course, this is always interesting. So since we're talking about unconsciousness, sleep is obviously a state of partial unconscious because you can be aroused, you can be stimulated and woken up, right? So again, your cortical activity in the cortex of the brain is slowed and depressed, but all your brainstem activity is still going on, right? So you still have major functions that are going on through the brainstem. So obviously, while you're sleeping at night, you don't have to think about breathing and you don't have to think about your heart rate. All that's taken care of through your reptile brain, right? Things like the medulla oblongata and the brainstem. Types of sleep. You have two major types of sleep that are defined by your EEG patterns that we can look at. You have the non-rapid eye movement or NREM sleep. And this is broken up into 4 different stages, which I'll talk about in just a minute. And then you have a rapid eye movement sleep, okay? Usually, you don't have to know the time frames for this, but I just put it because it's interesting. Usually, you pass through these kind of the first 2 stages that I'm going to talk about, stage 1 and 2 of your NREM sleep, during the first 30 to 45 minutes of your sleep. And then after that, you usually move into stages 3 and 4, which are going to be called your slow wave sleep. And these are oftentimes considered to be like restorative stages of sleep. Again, obviously, frequency of waves will decline, but the amplitude is actually going to increase, which is interesting. So you'll see this. Sometimes as you get into some of these deeper stages of sleep, your heart rate, respiratory rate, blood pressure can all change. So kind of interesting. At 90 minutes in, usually the 4th stage ends of sleep and you enter REM sleep. So your 4th stage of NREM sleep is going to end and you'll enter your rapid eye movement sleep, your REM sleep. And it usually begins pretty abruptly. So it kind of causes this kind of temporary paralysis, except for your rapid eye. Your eyes can be, again, moving, hence the name rapid eye movement. And a lot of times your oxygen consumption, your heart rate, and breathing actually increase. And they can actually even be greater than when you're awake. So I don't know if you've ever seen this on your kids, where they're like breathing like intently, and their eyes are moving and they're twitching. And so that can happen in REM sleep. Also, it's easy to picture this if you've ever, had your dog and your dog is deep, in their sleep, and they're like twitching and like breathing heavily. And so again, and most of our dreaming, as you can imagine, happens in our REM sleep. So again, like when your dog is running, okay, in their dream, they're in this phase. So again, these are just the typical cycles that you have. This is what your EEG looks like when you're awake. When you hit stage 1, this is when you're pretty relaxed. So you mostly are seeing like your alpha waves here. You can still be aroused very easily from sleep, but you're pretty relaxed. So again, you're more like the alpha waves. You're seeing the alpha waves for your EEG. Now in stage 2, you start to see some of these like irregular patterns. You still see some of these alpha waves, but then you have some of these irregular EEG spikes here. It's kind of short bursts. And arousal is a little more difficult here. You can still be aroused, but you might need a little shake here. Now when you hit stage 3, your sleep deepens and you start to see those theta waves, some of those theta waves. And our vital signs will start to kind of decline. And this again is where we see the theta waves that I told you that are uncommon in adult unless you're asleep. You'll see them in that stage 3. And then by the time you hit stage 4 is dominated by delta waves. Arousal is really difficult. So if you've ever had a kid that's been in stage 4, I have a child that we have to wake up in stage 4 sometimes because of some medical conditions, and it is really hard to arouse him. We can even get him out of bed and he will just collapse over. He's still asleep. We just can't seem to arouse him. That's more of that stage 4, and you'll see those nice delta waves. This is also where like bedwetting occurs. So if you have an older child and they all of a sudden wet the bed, it may just be that they are in stage 4 when their bladder was full and they just could not be aroused. It's not necessarily an issue unless it happens all the time. But it could just be that they were in stage 4 and the timing was just right. They really had to pee and they'd hit stage 4. They couldn't be aroused. The pain sensations from their bladder and the stretch sensations weren't able to wake them up because they were in this stage 4. This is also where night terrors can occur, and this is why I've had a child with night terrors. It is really challenging to wake them up from a night terror. That's because they're in this stage of sleep, and arousal is very difficult. It is hard if you've had a child with night terrors. They're screaming. You think they should be awake. They're screaming, and you cannot wake them, like you're shaking them. And then also sleepwalking occurs here. So stage 4. And then from stage 4, usually, again, you can go through these stages, and then you'll usually eventually hit REM sleep, which is your rapid eye movement. So again, your skeletal muscles, except for your ocular, your eye muscles, and the diaphragm are usually inhibited. You don't have a lot of muscle movement that's going on except for your eyes. And obviously your diaphragm so you can breathe. But again, that was just an automatic function, again, going through the brainstem. And most of your dreaming is going to occur in that REM sleep. Okay, so this is kind of your typical progression. I wanted you to see what your progression looks like. Obviously, you don't have to know this and what happens at different time frames. But what I wanted you to see is that, look at this REM sleep. So early on, you don't get a lot of REM sleep here. Early on, use hour 2 since you fell asleep, hour 3. And you kind of you'll cycle through like this every night. You'll cycle through. And then all of a sudden, you'll, hit about 4 hours and you start to increase the amount of time that you spend in that REM sleep stage. So that's why, again, you get more REM sleep, again, the longer that you sleep. And you'll see you don't even have to go through all the stages as the night goes on. So that's kind of your typical sleep progression. It's just interesting to see. And obviously, again, I talked about the stage 3 and 4 being kind of this restorative sleep. But people that don't get enough REM sleep, I'm probably in that category. Some of you probably are as well. And as the semester goes on, I'm sure you have felt this. I get very moody, and that's because I'm probably not getting enough REM sleep. And some of you probably feel that way as you're studying for exams and things like that. And then you can even sometimes start to feel depressed. So that REM sleep is important. It oftentimes, and it's actually really important for you when you are studying for exams. So try to make sure, especially the night before or while you're studying, that you do get enough sleep so you get some of this REM sleep. And the reason is that what this does is this gives your brain an opportunity to kind of analyze the day's events. It'll kind of process things and weed out some of the information that's unneeded. So again, eliminate some of that unneeded information synapses that were formed. It's kind of what we call dream to forget. And then work through kind of the emotional events or problems of the day. And sometimes, again, that's where you work through and commit some of this information to long-term memory. So this REM sleep is actually, believe it or not, pretty important in terms of especially the processes of learning and committing that information to memory. So there are sleep disorders. So narcolepsy is one, and you guys have probably all seen narcolepsy or at least seen memes or something on it, where like people will actually just abruptly like go into sleep. And this is not like, oh, I'm a little bit tired. Sorry about that. I had a quick interruption there. But the point of that is that narcolepsy is not like, oh, when you're tired and you kind of fall asleep. This would be like someone is like mid-sentence talking to you and then they just fall asleep. So it'll happen to them even when they got plenty of sleep the night before. So insomnia is obviously just kind of the opposite. This is the inability to be able to get to sleep. Oftentimes, usually it's falling asleep. That's the issue. And so, a person that has insomnia is unable to get like the proper amount of sleep or the proper quality of sleep, because remember that amount of REM sleep comes later in your sleep cycles. So sleep apnea is where people will actually temporarily kind of hold their breath during sleep. So they call it the temporary cessation, the stopping of breathing during their sleep. And so this causes some really irregular sleep and also makes it very difficult to enter again those REM sleep cycles. So sleep apnea can be very troublesome for individuals that have it. Okay, so we're going to leave sleep behind here and enter memory. So memory is obviously our ability to store information as well as our ability to retrieve that information, because it doesn't do us a lot of good to store that information if we're not able to retrieve it. And there are these different kinds of memory. You don't have to know all these different kinds of memory, but I put them up here just so that we do kind of categorize them. There's declarative memory, which is kind of our memory of facts, names, faces, words, dates. Procedural memory is going to be a memory of a skill with procedures, like playing an instrument. There's motor memory, which is going to be the memory of these motor skills, like riding a bike or, again, a skateboard or something like that. Again, you have that motor memory of how to do that. And then there's emotional memory, which is going to be memory of experiences that have a link to an emotion, such as, again, your heart pounds when you hear, again, the rattle of a rattlesnake or something like that. So those are just different types. So we're going to kind of primarily be talking about declarative memory. And there are two different stages of declarative memory storage. There's short-term memory storage, or what we call oftentimes our working memory, and we'll abbreviate it STM for short-term memory. And this is kind of a temporary holding place for information. It's usually limited to 7 or 8 bits or pieces of information. And so we're going to talk about this. You can either have like 7 individual pieces of information, or you can have 7 or 8 chunks of information. So we'll talk about how chunking is helpful, again, for committing things from short-term memory and then eventually into long-term memory. This is limited, again, to 7 or 8 pieces of information, like a phone number, okay? And again, it's going to involve some changes in neuron activity in those areas. Now, long-term memory has technically a limitless capacity. And we call this our LTM memory. And then this is where we actually are not just going to see changes in the activity going through those neurons. Like, again, those neurons have more activity when, again, we're accessing short-term memory. But our long-term memory not only will have more activity, but it also is going to have physical changes that happen in the neural structure. This is where neurons will move to innervate other neurons. So this is where we talk about that neuroplasticity of the brain and neurons making new connections with other neurons. That's what's happening in long-term memory. And this is where, again, we oftentimes say practice makes perfect. The more, again, repetitive information we get concerning that memory, the more likely we are to commit it to long-term memory storage. Okay, so let's talk a little bit more about this. So for example, committing things to short-term memory, we can use a system called chunking to help us, because again, remember, we can only commit about 7 or 8 pieces at any one point in time of information to short-term memory. So the best way to use our working memory or increase the capacity of our working memory is by using something called chunking. So for example, try to remember these letters: FBITWACIAIBM. Okay, now if I took away those letters, can you remember what those letters are? Most of you probably could not. However, what if we chunk them like this? FBI, TWA, CIA, IBM. Okay, so if you can chunk them together like that, and of course these kind of have meanings for us as well, right? If you can chunk them together like that, you are obviously probably now much more likely to remember that information. So chunking is, and any time that you can chunk that information into information that makes sense, okay, to us. So for an example, they grouped it here. So here, when they chunked the information, then they even grouped it on top of that. So you've got cat, hen for your animals, IBM, KFC for your companies, and XYZ, ABC for your alphabet. So you kind of created 3 groups there. Instead of having, each individual letter, which you just wouldn't be able to remember. So again, these are some really interesting ways to be able to help in terms of memory. This is why, again, anytime that you can chunk information in anatomy and physiology, you are more likely to be able to commit to short-term memory and then to long-term memory the more you practice it, okay? So chunking works. Chunk that information together. Also, this is where you can chunk information together using little mnemonics and tricks like that as well. So that helps with, again, committing some of this to short-term memory. Now, as we commit information from our short-term memory to our long-term memory, there are factors that help influence that transfer of information. And so one is our emotional state. So it's best if we're alert, you're motivated, you're surprised, you're aroused. Again, the more active and aroused the cerebral cortex is, the more likely you are to commit that information that you're studying from short-term memory to long-term memory. So again, this is sometimes where maybe it's not such a bad thing to have that cup of coffee that, again, is activating, keeping, again, the cerebral cortex aroused while you're studying. Also, rehearsal is huge. Again, repetition, repetition, repetition. And this is why, especially with anatomy and physiology, we're constantly telling you, use those flashcards, practice, practice, practice. Go through this information at the end of each week so that, again, you can commit that information to long-term memory. The more repetition you get, the more likely you are to commit that information to long-term memory. Association. Tie new information with old memories, okay? So if you're able to tie that information together with some old information and have that aha moment, you're more likely to commit that to long-term memory because you made that association. Also, again, there's this last one that doesn't really help you so much, but in terms of studying, but there is this part of your long-term memory called automatic memory. And it's where subconscious information is actually stored to your long-term memory. So, and there are some individuals that have like photographic memories that have a larger capacity for this automatic memory. So, for example, you may have been able to remember you had a lecture earlier today, and for some reason you get home and you can actually remember the pattern that was on your lecturer's t-shirt, even though you weren't consciously paying attention to that. Those are these types of things that can be, again, committed to long-term memory. So there are individuals that have these photographic memories, these abilities to form, lots of these automatic memories. And why the individuals are able to do that, we don't really fully understand. It's interesting. Now, long-term memories can change with time, meaning you can lose long-term memory. So again, this isn't a perfect scenario. It's not like once you've committed something to long-term memory, then it's committed there forever. This is constantly kind of changing with time. So our memory bank, if you want to consider it, kind of continually changes over time. And unfortunately, as you probably well know, our ability to not only store this information, but also to access it and retrieve it is going to decrease with age. Okay. It'll also decrease again with kind of like our emotional state. Like if you're really stressed out, it may make it really hard to retrieve this information. And so that's why a lot of times I'll tell you, take a break and relax if you're starting to feel stressed on the exam. I always give this example when I took a virology course as a graduate student, and the exams came in the form of 12 essay questions, all critical thinking. And so I would go through and I would look at the first question. I'd be like, I have no idea. I don't know what the answer is. Oh my gosh. And I get to the second one. I don't know that one either. And none of them were supposed to be questions that we could automatically answer because they were critical thinking ones. But I would start to panic. And then I remember having to stop and like, okay, let's just breathe for a minute. And then I'd go back down and look at it. And that way then I could then do that kind of higher processing that I needed to, and that retrieval of some of that long-term memory information that I needed to answer the essay questions. So if you ever find yourself in a bind on an exam, try that. Try to just stop for one moment, take a breath, slow everything down, and then kind of come back to it. Okay, it really does help you because you just can't do a lot of these higher thought processes when your fight or flight takes over. If you're in fight or flight mode, it is really hard to do these higher cognitive processes, especially again with retrieving that information. So again, here's kind of just the interesting process of memory here. A lot of times, again, it requires some outside stimuli, maybe visual you're studying, hearing, auditory, you hear, again, that lecture information. And you put that area in this kind of temporary storage in the cerebral cortex. And then if that, again, information is again processed at the right time, you can commit some of that information to short-term memory. Okay, so you select that data, all of this information. I mean, obviously you're not committing everything to short-term memory because like you're taking in a lot of information. You're not going to want to commit the clock ticking, right? Even though that sensory information is coming in to your short-term memory, storage, like the rate at which that clock is ticking, it's not important information for you at that time. So again, a lot of information is actually most of the information is actually getting deleted. And all of this, visual information, stimuli that you're taking in that you don't necessarily need is getting deleted. And then, once you have that information in short-term memory, okay, you need to commit it to long-term memory. And again, so maybe again, you are rehearsing over and over and over. You're using, StudyMate flashcards. You're going through your notes over and over again. Then that's going to commit some of that information to long-term memory. Also, again, if you're excited about the information, you're more likely to commit it to long-term memory. You find it fascinating. Or you can associate that information with some type of an emotional response. Again, relate it to you and your body. Think about how it relates to you. May help you to form an emotional attachment to that information and commit that information to long-term memory. So those are some tricks that you can do again with also, and associating that new material with some old material will also help you to commit to long-term memory. So I kind of put this memory processing in the form of studying for anatomy because that's what's probably most important to you right now. Interesting in terms of obviously damage to certain areas associated with memory. So damage to the hippocampus or some of the surrounding temporal lobe structures that are going to be associated with the hippocampus on either side result in slight memory loss. And if you happen to have bilateral destruction of those areas, this can cause really widespread amnesia. So let's talk about some of the different types of amnesia. So, and this is what really I want you to know: anterograde amnesia and retrograde amnesia. So anterograde amnesia is where your consolidated memories are not lost, but new ones. You basically can't make new memories. So you can have old memories, but you can't make these new ones. So the person kind of lives in the here and now. So this is the movie 50 First Dates, okay? So Drew Barrymore, right? She has this anterograde amnesia. She's unable to form these new memories. And so memories of conversations from just 5 minutes ago before aren't able to be remembered. So for example, you can meet this individual, you can talk with this individual and have a normal conversation with them. But if they leave the room and walk back in, then they will have no recollection of the conversation that you just had them. So you have to meet them all over again, okay? So it really interesting type of amnesia. Retrograde amnesia is more of the case like that you'd see in Overboard, where you have a loss of memories that were formed in the past. Who am I? What am I doing here? You don't remember anything from the past. You can make memories going forward, but you are not unable, even if just temporarily, you're unable to pull up that information from the past. So kind of interesting. I'm not going to go through these protections of the brains because we already went through them. Again, you have bone, meninges, and cerebral spinal fluid. Remember that those different meninge layers are the dura mater, the arachnoid mater, and the pia mater. I used to have this at the end of the lecture, but I ended up moving it up to the beginning of lecture because we talked about movement of cerebral spinal fluid. But obviously, all of those things protect the brain. And then this is just kind of some interesting information on traumatic brain injuries and the difference between concussion, contusion, and laceration. So a concussion is kind of a temporary alteration in function of the brain. And usually this is oftentimes due to a hit on the skull or the brain. So, and it's usually in the posterior region because for some reason this area is typically more associated with concussions if you were to hit the back of your head versus the front. It just has to do with some of the protections associated with the brain. So, again, it'll sometimes result in temporary loss of consciousness, headache, drowsiness, sometimes also vomiting can occur, confusion, lack of concentration. Usually the headache, I've actually had a concussion, the headache is pretty severe. It's not like your average day headache. It's that one that you just want to split your head open, that kind of nasty headache. And but again, this is a temporary situation. Now, a contusion is if you've had kind of a more severe concussion, which is some severe bruising of the brain, and it's usually more a permanent damage type situation. So this can happen, and this is where if you've had multiple concussions that, again, resulted in contusions, bruising of the brain, then this is where you start to see kind of the damage add up with multiple kind of concussions and technically contusions to the brain over time. And so this is oftentimes you lose consciousness, but less than 5 minutes. And oftentimes you'll see blood in the cerebral spinal fluid, and that's because of the bruising. You actually bruised the brain. You actually did damage to the soft tissue in the blood vessels have broken in that soft tissue of the brain. And so again, because you broke blood vessels and now you have areas of the brain that aren't getting enough blood flow, that's where you can get some of that permanent damage. And then a laceration is actually tearing of the brain. So again, you actually like fracture the brain. You have like an object that impales through that tissue or bullet. Again, that lacerates or tears the brain. And obviously this oftentimes results in an increase in intracranial pressure from, again, the damaging of all the blood vessels from that laceration. You can have something also that's called a subdural or subarachnoid hemorrhage. We call it subdural because it happens below the duramater, which is in that subarachnoid space. And what ends up happening is, obviously, if you have quite a bit of damage, the blood vessels and you're hemorrhaging, some of those arteries are hemorrhaging and putting out a lot of blood. They can actually put too much pressure on the brain. And if they put too much pressure, this is why a subdural hemorrhage becomes an immediate situation, in that you need to relieve that pressure as quickly as you can, because you can see you're actually going to be putting pressure on the brain itself. And it can put so much pressure on the brain itself because, again, it's trapped by the cranium there, that you can actually push the brainstem through the foramen magnum, and that will result in death, as you can imagine. So again, this is why this is such an immediate situation. We had a friend of ours that actually fell from like a third story of a building, and he survived, but he ended up having a subdural hemorrhage, and they had to immediately drain it. He was lucky to have survived. Cerebral edema is where you actually get swelling of the actual brain associated with a head injury. And again, that swelling of the brain can cause problems, again, as it can decrease blood flow and things like that to certain areas of the brain as the brain swells. So that's cerebral edema. CVAs are referred to as strokes. I know I've already kind of talked about CVAs a little bit when I've mentioned that they were strokes, but technically we call the more clinical term for a stroke is a cerebrovascular accident. That's a CVA. And it's usually due to some type of ischemia, meaning that tissue was deprived of blood. So the brain tissue was deprived of blood. Oftentimes it's because of a blockage of a major artery that's feeding that area. So you can have a large clot, and that's what usually causes the majority of CVAs in older individuals. And then what ends up happening, this is more than you need to know, but it's kind of interesting, that glutamate actually causes this to be worse. It kind of excites the cells that are already being deprived of oxygen, kind of on their way out. And as it excites them, they kind of disintegrate faster than they normally would with that. Remember, glutamate's an excitatory neurotransmitter. So it actually can cause problems as you get this kind of flooding, this tidal wave of glutamate. And that tidal wave of glutamate is released when there's damage to the brain, which is unfortunate. So it's kind of counteracting for us to have that glutamate released, tidal wave released, unfortunately, when we do have damage to the brain. And it does oftentimes cause issues. And then hemiplegia is just paralysis on one side that we usually see, again, with a CVA. If you have a CVA on the left hemisphere of the brain, then it oftentimes will cause that hemiplegia paralysis on the right side of the body. It may result in speech deficits on the right side. So this is what you're seeing here in this individual that's had a CVA. So again, you can see the paralysis on the left side here. So that means the damage is in the right cerebral cortex here. So again, remember, because of that decussation that occurs at the medulla oblongata. TIAs, you can read about those. I'm not going to talk about those too much. Transischemic attacks, they're kind of like mini strokes, and they usually, again, are temporary. They're usually reversible. You don't have permanent damage to them. And then TPA is kind of, this should be a lowercase t. It's usually a lowercase t. Tissue plasminogen activator is the only approved treatment for strokes. They give it early on if someone is showing signs of a stroke, because it actually can dissolve the blood clots that have formed in the brain that are causing the stroke. So kind of interesting. And then here's just on Alzheimer's disease. Again, interesting. I'm not going to test you on Alzheimer's, but you can read about it. It does oftentimes happen because we get these proteins that are misfolded, and they end up they're amyloid, beta amyloid peptides, and when they become misfolded, they will actually cause these plaques to form in the brain of all these, because they'll help other proteins misfold as well. And so we call them these amyloid bodies or amyloid plaques. Now, what's interesting is normally these amyloid peptides will kind of get filtered out at night while you're sleeping. Remember, because they'll be filtered out through the cerebral spinal fluid. We talked about that. And so this is why, again, sleep is important in terms of potentially, helping to prevent Alzheimer's disease. Again, there's obviously a genetic component to that, and there's a lot that we don't understand in terms of Alzheimer's disease, but they do think that sleep is a component of that, because we do, our body does filter out some of those amyloid bodies at night. So, and again, what ends up happening is as we form these plaques, these beta amyloid plaques, then the brain actually starts to die in certain areas and it shrinks. So this is a normal brain and this is an Alzheimer's brain. So sorry, I didn't mean to quite go that long, but there's just so many interesting things to talk about with the brain. So please let me know if you have any questions or concerns, and then we will have a quiz on this. Look for the announcement for the date for that quiz. I am going to push it back a little bit.